Good day, bright physics students. So, in this video, we will be discussing Introduction to Classical Mechanics, or particularly, we will focus more on a sub-branch of classical mechanics known as kinematics. So, what is classical mechanics? Classical mechanics are also known as mechanics, or in other references, it's also called as Newtonian mechanics. So before we proceed with the definition of classical mechanics, let's try to reason out why it's also called Newtonian mechanics. A lot of topics or lessons that you would definitely found in a classical mechanics subject are contributions of Sir Isaac Newton. So in honor of the contributions of that great man, um, it was also named after him. Now, you would ask, why do we still need to study classical mechanics even though it's classical? So, um, although there are lots of changes that's happened all throughout the century in the field of physics, because as we all know, for massive objects in the universe, there's relativistic physics, and for very small objects in the universe, there's quantum physics. So, why is there still a need for us to study classical mechanics? Because um, a lot of applications in engineering, the way that we build different structures, or even um, the motion of every object that you would see in a normal day is described in classical mechanics. All right. So what is the definition of classical mechanics? So classical mechanics is a branch of physics that deals with the motion of bodies. So we're talking about motion itself of what? Of different bodies. So in classical mechanics, we have two different type of bodies. Right? So first one would be the point masses, and the second one is the rigid objects. So when we say point masses, these are very small objects, or infinitesimally small objects. So basically, we're dealing with the motion of molecules or atoms. How about rigid objects? Rigid objects, these are large objects that rotate but they cannot change their own shape. So essentially, these are maybe the heavenly objects, such as a natural satellite, just like our own moon or our own planet itself. So they rotate, but they cannot change their own shape. So they're very large objects. Now, a little disclaimer: although there's no such thing as a perfectly rigid object or a truly point mass object, but by doing so, by approximating them as such, um, classical mechanics can accurately describe the motion of objects from the very small object, which are molecules, up to the very large object in the universe, which are galaxies. Okay, now going back to our discussion, as mentioned earlier, a sub branch of classical mechanics would be the focus of our discussion, and that is kinematics. So kinematics is a branch of mechanics, obviously, but this time kinematics focuses on the motion of the object. So focus is on motion. So the course of motion. Alright. So if the focus is on the course of motion, so let's give an example. So let's say this is you, and then you kick a ball. So this ball rolls from that point up to this point. Now, if we're dealing with kinematics, we're only trying to understand the course of the motion. So we do not care why does this ball move in the first place. So we don't care if you try to kick it, or um, you just nudge it. So yeah, you don't need to understand the cause of motion, but rather you'll focus on the course of motion itself. So what does this ball do? Does it roll or does it bounce? So that's your that's the focus of motion. That's the focus of kinematics. All right. So aside from kinematics, there is also two other sub branches of classical mechanics. So the other one is statics. So statics, our focus is on objects in is on objects that are in a state of equilibrium. So objects in equilibrium. So why are objects in equilibrium such a thing in statics? Because in statics, we will deal with objects that are not moving. So since they attain a state of stability, they are obviously in equilibrium, and we'll try to understand why are they stable, or why do they not move. All right, so that's on statics. So lastly, the last branch of classical mechanics would be dynamics. So dynamics, if a while ago in kinematics the focus is only on the course of motion, as for dynamics the focus is on the cause of motion. All right, so if we try to use the previous example, you kicking the ball. So since the cause of motion is you kicking the ball, so we wanted to understand how much force did you exert in order to kick the ball. Alright, so basically we'll deal with forces in here. Alright, so again, there's three sub branches of classical mechanics. Number one is kinematics, then statics, and then dynamics. So now, since we will deal with kinematics first, we shall understand motion itself. Alright, so in order to understand motion itself, we need to know the different types of motion first. So what are the different types of motion? The first one would be translational motion. So translational motion happens when a body shifts from one point to another. So there are two subtypes of translational motion. Number one is rectilinear, and the second one will be curvilinear. So in this example, the Angry Bird was launched into space and then it traveled a straight path. So definitely this one, this Angry Bird shifts from one point to another. So this is a translational motion, but particularly this is rectilinear motion, because again the path traveled by the object is straight path. How about this one? Okay, this one, the man throws an object in midair, and then it lands into another position. So essentially they're the same, right? This one man, the object traveled from one point to another, just like the Angry Bird, but the difference is the path traveled by the object. So as you can see, the path traveled by the object in here is called as the trajectory, and the trajectory is parabolic in nature or curved. That's why this one, although it's translational, this one is curvilinear motion. Alright, so next, second type of motion would be rotational motion. So rotational motion happens when a body rotates around a fixed axis or about a fixed axis. So there are also two types, rotatory and circular motion. So this one is rotatory motion. So when a body moves around a fixed axis, so that's rotatory motion. And circular motion happens when a body moves about a fixed axis or about another object. So that is circular motion. Alright, and the last one would be periodic motion. So periodic motion happens when a body wiggles about a fixed position, or vibrates or oscillates about a fixed position. So definitely it won't budge, or it won't try to move into another position, but just wiggles on that fixed position. So what are the most um, excellent examples of periodic motion? So this one right here, this is a simple pendulum. So it was attached in this stick right here. So the pendulum doesn't get away from that point, but it wiggles on that fixed position. So this is an example of periodic motion. And this one, so the particle moves up and down on that particular two-dimensional plane, and now it gives us this wave-like motion. So it oscillates and then produces this wave-like motion. So this is definitely an example of a periodic motion. So I'll review. We have three different types of motion. Number one, translational. Second is rotational motion, and the third one is periodic motion. All right. So the next thing is that every time that we're going to deal with classical mechanics, you would definitely see a lot of this one, particle model. So what is a particle model? Particle model describes the moving object as a particle regardless of its size. So just like this one, a car traveled from its initial position up to its final position, just like this one. Now, the question is, if we're trying to measure the distance or the displacement of this car, where do we want to measure it first? On the tail of the car, or on the bumper of the car, or on the middle of the car? So where do we start our measurement? Because it's too large, all right? So in order to eliminate that kind of error, we can associate this car into using a simple particle. Alright, so instead of using different objects, we will use a particle, and that particle will now mimic or copy the motion of your object. And in this way, it will be definitely easier for us to track where is the direction of the velocity vector, or the acceleration vector, or even the displacement of your object. All right, so these are all the things that you could make easier if you use the particle model. Okay, so next, aside from the particle model, there's a lot of alternative representation of your data. All right, so you can use tabular presentation, pictorial, or graphical presentation of your data. So let's start with tabular presentation of data. In a tabular presentation of data, the numbers are already exposed. So there are two variables, and then the data is already presented in this way. So just like this one, at time 0, which is the initial time, or the time that you start your observation, you can definitely see where is the position of the car, right? So the problem with this one is that you cannot directly visualize where is the car at this instant. All right, although you can definitely see the relationship of the values in here, but again, you cannot directly see it. Unlike when we use a pictorial presentation of data, just like this one, so it uses pictures. So definitely, if you're a very visual type of learner, this one's the very best for you. But I suggest that you will you will practice using graphical presentation of data, because in a graphical presentation of data, um, the relationship of variables are already presented, and just by merely looking at it, you could make an interpretation of what is happening um, in or what is happening inside um, the problem, or what is happening um, in the two variables. Are they correlated with each other? So these are the use of graphs. All right. So the big concept, or the big idea behind this, is that we need to um, strengthen our knowledge of graphical presentation of data, because it brings about a lot of mathematical interpretations, and that's how most physicists use graphs to to interpret what happened, or what happens in a specific problem. All right. So just like this one, in discussion of kinematics, you would definitely see these three graphs. So the first graph is what we call as the position time graph. So let me just write it here, position time graph. The second graph in the middle part is what we call as the velocity time graph. And the last graph on the bottommost part is what we call as the acceleration time graph. Acceleration time graph. So before we proceed on interpreting parts of this graph, we need to identify first what are the variables used in this graph. So as you can notice, a variable that doesn't change in these three graphs is the time variable, because time is the only thing that moves forward. It doesn't even move backward. Right? So in order to justify the constancy of the time variable, we need to put it in the x-axis. So this will be the time variable, and the time variable. Alright, how about the position time graph? So as for the position time graph, the y-axis will be obviously the position x. As for velocity time graph, the y-axis is the velocity v. And as for the acceleration time graph, it will be the y-axis will be the acceleration. All right. Now, in interpreting these three graphs, because they're correlated with each other, what happens with the first graph, there would definitely be an effect in the second graph and in the third graph, obviously. All right. So what I wanted you to do is that you need to look at these two parts. So the first one will be this one, and the second one is this one. All right. So the first one, the ones that's in a box. So, if you try to look at it, the changes happening in the y-axis, or in the position x, as time progresses is very drastic. All right, this is very drastic changes. So what happens now then to velocity time graph when position time graph y values are drastically changes? So this is what happens with velocity time graph. So as for the velocity time graph, it becomes linear. So the change is constantly happening for y values, and that is the velocity, right? So every time that is a constant change happening in velocity, what happens to acceleration? Acceleration now becomes constant value, constant acceleration value. All right, so it becomes a plateau. Now if you try to look at this one, the ones encircled right here, so as for the position time graph, the y value, or the position x, is now linear in nature, meaning the changes happening in position x is constant. There is a constant change happening in position x. What is now then the effect for velocity time graph? So the effect for the velocity time graph, if you try to look at it, there is a constant y value all throughout the time frame. So constant y value or constant velocity value. And what now then happens to acceleration if velocity is now constant? Acceleration becomes 0. Okay, so just like what we did in this slide, this one's also pertaining to that. So in order to strengthen our knowledge about that and to emphasize what happens in those graphs, so this one is the best presentation of that. So position time graph, if in the position time graph the y values are drastically changing, so drastic changes in y value as time progresses, definitely. So what happens to velocity time graph? It becomes linear. Alright, so linear meaning there is a constant change in y value as time progresses. Alright, so constant change in y value. And now, since the graph for velocity time graph becomes linear, as for the acceleration time graph, it now becomes a plateau or constant. So constant y value. So there's no changes happening in the y value. It's a constant y value. So as time progresses, the y value doesn't change at all. Alright? So that's what happens. Next, how about if the position time graph becomes linear? So again, if it's linear, the y value is constantly changing. Again, y value constantly change. So what happens to velocity time graph when the position time graph is already linear? So as for the velocity time graph, this becomes constant. So constant y value. So since the velocity here isn't changing at all, it's constant, right? So what happens to acceleration is that it becomes 0. 0 what? 0 y value. Okay? Because the time still progresses. And now, what if the position time graph is constant already? So constant y value. So what now happens to velocity time graph? So velocity now becomes 0 in nature, so 0 y value. So since there is no velocity at all, definitely acceleration would also be 0. Okay, but again, time doesn't stop. Time always moves forward. So still, the only thing that's 0 is the acceleration, which is the y value. Alright, so that's how we interpret graphs in this context. Alright, now in interpreting graphs, there's two things that we need to understand first. First one would be the slope of the line, and the second one would be the area under the curve. So let's deal first with the area under the curve. So there's two graphs present in here. The first one would be the velocity time graph, and the second one is the acceleration time graph. So what happened to the position time graph? So if we try to reason out what happened to the position time graph, let's look at the topic first. So since this is the area under the curve, let's try to find first the general formula for area. So area is a two-dimensional formula, right? So now, the general formula for area would be the product of its two sides. So basically, its base and height. Now, in these graphs, we can draw straight lines in order for us to cut out the whole graph into different sections. So this is section 1, section 2, section 3, section 4. Now, these are different shapes, right? These are different cutout shapes, and since these are very basic shapes, you can definitely solve for the area of this one. This is the area of a triangle, the area of a square, a triangle, and a triangle. Alright, now as we go on, we can now solve for the different areas by using their own formulas. And to solve for the total area under the curve, you just need to add the individual areas in here. So right now, the question is why is the position time graph not included? Because it doesn't have a physical relevance. So why is that? If we try to look at the velocity time graph, so let's write it here, velocity time graph. So since the general formula for area would be base times height, so the base is definitely the time, and the height would be the y-axis, so that's velocity. So let's use units in order for us to identify what would be the physical quantity that's present as the area under the curve for each section. So as for the velocity time graph, the base is in seconds because it's time, and the height is in meters per second. So we cancel out the second unit, okay, and we're left with the meters, and meters is a unit of position x, or displacement x, or distance. Alright, so definitely if we're trying to solve for the area under the curve of a velocity time graph, what we're getting is position x. Alright, so this is x sub 1, x sub 2, x sub 3, and x sub 4. So again, if we're trying to solve for the area of x sub 1, definitely you'll use the formula for the area of a triangle, and for x sub 2, you'll use the formula for the area of a square, x sub 3, area of a triangle, x sub 4, area of a triangle. And now, how do we solve for the total area under the curve? Just get the sum of all the areas. So how do we do that? This will become x, right? This is x. To solve for the area under the curve, which is that's x, x is equal to the sum of the individual areas, where I is equal to 1 up to n. And what is the formula of area for velocity time graph? So the formula for area of a velocity time graph is velocity times time, where again I is equal to 1 up to n. So this is the formula for velocity time graph. Now, how about acceleration time graph? So what is the physical relevance of finding the area under the curve for an acceleration time graph? So as for the acceleration time graph, so again we use the units. So as for the base, it's second, and as for the height, it's in meters per second squared. And as we cancel the unit second, okay, but this one, the unit second in here is in the second degree, so we will be left with another second. So the final unit that we will obtain is meters per second, which is the unit of the physical quantity velocity. So in an acceleration time graph, if we're trying to solve for the area under the curve of it, we will be left with velocity. So this is v sub 1, v sub 2, and v sub 3. Alright, so again, just like what we did with the velocity time graph in here, if the graph is a basic type of graph, so in order to solve for the total area under the curve, you need to just get the sum. So this is the total area under the curve of an acceleration time graph. So you need to get the sum of the individual areas from I, which is equal to 1 up to n. And again, the formula for area inside an acceleration time graph will be the product of acceleration and time, okay, where I is equal to 1 up to n. So that is the formula for, again, the total area under the curve for each graph. So how about the position time graph? So as for the position time graph, so the base would be in seconds, obviously, and the y-axis, the unit there is in meters. So we're left with the unit meter second, and there's no such thing in physics that that will have the unit meter second. So obviously, it doesn't have any physical relevance at all. Alright, so you don't need to solve for the area under the curve of a position time graph. Alright, so now, the question lies with this one. So these are basic graphs, right? These are basic graphs. What if our graph now looks like this one? So yeah, just like this one. So how do we solve for the total area under the curve of that type of graph? So let's try to use the technique that we did with this one. So we draw straight lines below the graph, okay, and we try to attempt to like cut out this shape into basic shapes, right? So if we try to put straight line in here, so we will be getting the area of this one, because definitely this is just a rectangle, right? But as for this one, this isn't a perfect triangle because it's curved on the part of the hypotenuse, or the supposed hypotenuse of the triangle. So since it isn't a perfect triangle, it's a curved one, okay, we can't really solve for the total area under the curve by using that kind of approach. So what will we do is that we try to shorten the width of our triangle, or rectangle rather. So we try to shorten the width of our rectangle up to the point wherein the space above those rectangles will now be negligible. And how is that? So we can actually make our rectangles very small, or infinitesimally very small in width. All right, so that the space above the rectangles that will be that we have some sort of a problem a while ago will now be negligible. But how do we solve for the total area under the curve? So we still use summation. Do we still use summation? No, because it would be very hard for us to find the sum of all the areas of infinite numbers of rectangles, right? So in order to solve for the total area under the curve of a velocity time graph, we can use integral or integration. So we'll use integral. Okay, integral of what? Integral of v of t, the function of velocity with respect to time, dt, with limits from t sub 1 to t sub 2. Alright, so it's just like what we did with this one, but this time we'll be setting a limit Okay, so this will make our lives very easy as we solve for um, the total area under the curve of this types of graph. So just like what we did with the velocity time graph, this one will also do that. So in order to solve for the total area under the curve of an acceleration time graph, but this time if the acceleration time graph looks like this one, so we will use this formula, integral of a of t, the function of a of t dt, with limits from t sub 1 up to t sub 2. So again, when do we use the formula of summation? We'll only use this if the graph is a basic type of graph. So graph is very basic, just like this one, that you can cut it out into different sections of geometric figures. And we will use integration if the graph is curved. Alright, so this one's also doing that. So graph is basic and graph is curved. Alright, so that's how we do the area under the curve. So these are the formulas of different areas that you could definitely found under the curve of a basic graph. Okay, so it's important that you memorize these ones. Now, aside from the total area under the curve of a graph, the other thing that that we need to identify in order to understand the graph itself is the slope of the line. So what is the formula for the slope of the line with 2 points? So slope of the line with 2 points, m is equal to rise over run. Right? So rise is the y-axis and the run is the x-axis. So this is y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So that's the formula for the slope of the line. And we will just pattern our formula for velocity with the formula of the slope of the line. But before we do that, let's try to define first what is average velocity. So average velocity is the ratio between the displacement delta x and the time interval. So the time interval is obviously in the x dimension, and the delta x or the position x will be found in the y direction. So this is position x, this is your time variable. So according to our definition of velocity, so we will associate, or we will try to get the average of these two the average velocity between these 2 points. Velocity is also defined as the rate of change in position. So again, the rate of change in position. So again, we will just pattern our formula for average velocity with our formula of the slope of the line. So this one will be our equation. So average velocity is equal to, so the ones in the numerator will be the variable in the y-axis, and that is our position x. So that's x sub 2 minus x sub 1. But since we've already used it in our mathematical equation getting the slope of the line, so instead of using subscript 2 and 1, we will use subscript final and initial. Alright, so this one will be x sub f minus x sub I all over, so our run will be the variable in the x dimension, and that's our time variable. So this will become final time minus initial time. And every time that you see final minus initial in your equation, that means there is a change happening in that specific variable. So we can use the symbol delta, because delta means there is a change happening. Alright, so if there is a change happening, again, that's our mathematical interpretation of that is final minus initial. So this will be delta x all over delta t. Alright, so that's our formula for average velocity. Now, how about instantaneous velocity? So when we say instantaneous velocity, we try to find the velocity of a particle at a specific point of time. So unlike what we did with this one, with the average velocity, we try to get the velocity of 2 points. Okay? The particle with 2 points. But this time, in instantaneous velocity, we're only given 1 point in the graph. Alright? So how do we solve for instantaneous velocity? So what we'll do is that we try to get the limiting value of the ratio of delta x as delta t approaches 0. So in mathematics, we try to approach point P. This is the position of the particle, all right, with another point which is point Q. So point Q now approaches point P. So as point Q approaches point P, our time variable becomes really small. That's why it approaches 0, because that's the start of your observation, right? So to solve for instantaneous velocity, this will become the limit of delta x over delta t as delta t approaches 0. And as we all know, in mathematics, we don't want a 0 value in our denominator, because it will then give us an answer that does not really exist at all. And in physics, we don't want that. So in order to eliminate this problem, we can use L'Hopital, or simply get the derivative, the first derivative of position x. So this will become dx over dt. Alright, so if we're trying to get the instantaneous velocity of a particle, simply get the first derivative of position x with respect to time. Alright, how about acceleration? So just like what we did with average velocity, we'll pattern our formula for average acceleration with the slope of the line. But before we do that, let's define first what is acceleration. So acceleration is defined as the rate of change in velocity. So this is the rate of change in velocity, or it's simply the ratio between the change in velocity, delta v, to the time elapsed during this change in time. So again, this our graph is the y-axis, the y variable in our graph would be the velocity, the velocity variable, and the x variable in our graph will be the time variable. So by patterning this one to our slope equation, so our formula for average acceleration is equal to, so again, rise over run, so that's y, right, the y variable, so that's v sub f minus v sub I all over t sub f minus t sub I. Or again, there is a change happening in this variable, also in this variable, so we can simply rewrite this as delta v over delta t. Okay, so that's our formula for average acceleration. And lastly, how about instantaneous acceleration? As for the instantaneous acceleration, again, what if we're left with one point in the graph? Because in instantaneous acceleration, we wanted to identify the acceleration of a particle at a specific point of time. So definitely it's just 1 point. Alright, so how do we solve for the instantaneous acceleration? So in order to do that, you just simply get the first derivative of velocity with respect to time. So instantaneous acceleration is equal to the limit of delta v over delta t as delta t approaches 0. And again, this becomes the first derivative of velocity with respect to time. Now, since we all know that velocity is the first derivative of position x, right? So, what if we're given a function of x with respect to time, and our task is to identify the instantaneous acceleration of that particle? So, in order to do that, you need to get the second derivative of position x with respect to time. So, this is the formulas for instantaneous acceleration. So, let's try to answer some problems. So, example problem number 1. The position of a particle moving along the x-axis is given by the function x of t is equal to 3t squared plus 5 with time t in seconds and position x in meters. So, the task is to find the average velocity from time, which is equal to 1 second to 3 seconds, and B, instantaneous velocity at 1 second, at 2 seconds, and at 3 seconds. So let's try to answer letter A first. So in order to find the answer for letter A, so again, what is the formula for average velocity? The formula for average velocity will be average velocity is equal to delta x over delta t, where delta x is equal to x sub f minus x sub I over t sub f minus t sub I. So as for letter A, the final time and the initial time are already given. So you can write it down immediately. So final time would be obviously 3 seconds. So 3 seconds minus 1 second. So how about the position, final position and the initial position of the particle? So in order to do that, let's go back to the original problem. So the original problem gave us a function of time. A function of x with respect to time. So x of t is equal to 3t squared plus 5. Alright. So what will we do to find the final position x and the initial position x? So let's write here initial position x. So since this is a function of time, so we can substitute the initial time inside to solve for the initial position x. So this is also equal to x of 1. So x of 1, that means this is 3 times 1 squared plus 5. So this is equal to 3 times 1, because 1 squared is equal to 1. So 3 times 1 is 3 plus 5. This gives us a value of 8. And position x is in meters. So we can use meter in this answer. Alright, and as for the final position x, this is also equal to x of 3, and this is equal to 3 times 3 squared plus 5. So 3 squared is equal to 9 times 3, 27 plus 5, that's equal to 32. 32 what? 32 meters. So we can now write it inside our solution. So the final position x is 32 meters minus 8 meters. So this gives us an answer of 32 minus 8 is 24. 24 meter all over 2 seconds, which then gives us a final answer of 12 meters per second. So since this is velocity, and velocity is a vector quantity, so you need to indicate the positive sign to know that the direction of the velocity vector could either be to the right or upwards. And but it since it's not mentioned in the problem, so just indicate the positive sign. All right, and that's our final answer for letter A. So that's positive 12 meters per second. All right, so how about finding the instantaneous velocity at 1 second, at 2 seconds, and at 3 seconds? So how do we do that? So remember that the formula for instantaneous velocity is the first derivative of position x with respect to time. So if it's the first derivative of position x with respect to time, okay, let's try to first get the function, the original function given to us. So the first function is x of t is equal to 3t squared plus 5. So try to get the first derivative of this function. So x of t prime. Alright, so the first derivative of this function will be 6t. Okay, so since this is a constant, it will become 0 then. So now that we have our derived function, we can now substitute each values. So at 1 second, so just substitute this one. So x of 1 prime, so this is 6 times 1, and x of 1 prime is equal to 6, and the unit is in meters per second, obviously. So 6 meters per second, this is positive. Alright, at 2 seconds, so just substitute 2 inside. So x of 2 prime, this is 6 times 2. So this gives us a value of 12 meters per second. Again, positive 12 meters per second. And at 3 seconds, so this is x of 3 prime. This is equal to 6 times 3. So our final answer would be positive 18 meters per second. So these are our final answers. So at 1 second, the particle is at 6 meters per second velocity. At 2 seconds, it's already at 12 meters per second velocity. And at 3 seconds, the particle is at 18 meters per second velocity. So going back, what did we do first? So to solve for the instantaneous velocity, you need to find first the derivative of the position x, the function x with respect to time. So in order to do that, what do we need to do is that you need to copy the exponent and multiply it to the coefficient. So 2 times 3, which then gives us 6. Now, as we do that, we will now subtract 1 to the exponent. So this becomes, this is now equal to 1, alright? So instead of writing 1 in here, so yeah, it's already understood that 60 is also raised to 1. And again, constants, if you try to get the derivative of a constant, it's equal to 0. Alright, so that is our example problem number 1. So I hope that in finding the average velocity and the instantaneous velocity, everything is clear. Okay, so now let's proceed with example problem number 2. So as for the example problem number 2, the given function is velocity with respect to time function. So the first thing that we need to do is to solve for average acceleration, and then instantaneous acceleration, and then the area under the curve if t sub 1 is equal to 1 second and t sub 2 is equal to 2 seconds. So let's try to solve for the average acceleration first. So average acceleration, the formula for average acceleration is delta v, change in velocity with respect to time, so delta v over delta t, or this is equal to final velocity minus initial velocity all over final time minus initial time. So again, our final time and initial time is already given in the problem. That's 1 second and 2 seconds. So 2 seconds minus 1 second. Okay, although it's not literally mentioned in the problem that 2 seconds is t sub 2, I mean final time, although it's t sub 2 in here. So this is our final time because again time only moves forward, it doesn't move backward. Alright, so 2 seconds minus 1 second. So how about our final velocity and initial velocity? So just like what we did with our earlier problem, so get the initial or the original function. So v of t is equal to negative 4 t squared plus 2t. Alright, so now what we would do is that we just substitute the initial time and the final time inside our function, but separately. Alright, so let's try to solve v of 1 first. So this becomes negative 4t, so 1 squared plus 2 times 1. So obviously this is 1 squared, so just 1. Negative 4 times 1 is negative 4 plus 2 times 1. So negative 4 plus 2 gives us v of 1 is equal to negative 2. Alright, so although it's not mentioned in here, so let's just assume that the velocity is in meters per second. Alright, so this becomes negative 2 meters per second. So it's alright that we've obtained a negative value for the velocity. How about the second one? So our final time, so v of 2 is equal to negative 4 times 2 squared plus 2 times 2. So this is equal to 2 squared, that's 4. 4 times 4 is negative 16. So negative 16 plus 2 times 2 is 4. So v of 2 is equal to negative 12 meters per second. Okay. So what happens then to our final velocity and initial velocity? So obviously v of 1 is our initial velocity and v of 2 is our final velocity. So just substitute what we've gathered in these two solutions. So final velocity is negative 12 meters per second, okay, minus our initial velocity, negative 2 meters per second. So this will now give us a value of, so again this is negative preceded by a minus sign, so this will become positive and plus. So negative 12 plus 2 gives us final answer of negative 10 meters per second as the numerator, and as for the denominator, 2 minus 1 is 1 second, and our final answer is now negative 10 meters per second squared. So this is now our average acceleration. Alright, so I hope there's no questions at all, because it's just like the ones that we've done with the average velocity. Okay, so how about the instantaneous acceleration? So as for the instantaneous acceleration, the formula for instantaneous acceleration will be the first derivative of velocity with respect to time, or the second derivative of position x with respect to time. But this time, the given function is a velocity with respect to time function. So just get the first derivative of this function first, and then substitute the values of t sub 1 and t sub 2. Alright? So if the function is v of t is equal to negative 4 t squared plus 2t, so get the first derivative of this function, so v of t prime is equal to, again, what we do is that we try to copy the exponent and multiply that to the coefficient. So 4 times 2 is 8. but since it's negative, so negative 8, and then subtract 1 to the exponent, so negative 8t, plus, this time, although it's not written in here, the exponent of this 2t is 1. Alright, so 2 times 1 is obviously 2. But this time, since we've already subtracted 1 to the exponent, so we're left with 0. So the variable is eliminated. Okay, so we're left with this one, the function. Okay, the v of t prime function is negative 8t plus 2. So to solve for the instantaneous acceleration at 1 second, so at 1 second, so v of 1 prime is equal to negative 8 times 1 plus 2. Okay, which then gives us an answer. So v of 1 prime is equal to negative 8 plus 2, that's equal to negative 6 meters per second squared. Alright, so instantaneous acceleration, that's meters per second squared. And at 2 seconds, so at 2 seconds, that's v of 2 prime. So v of 2 prime, this is equal to negative 8 times 2 plus 2. So v of 2 prime is equal to negative 8 times 2, so that's negative 16 plus 2. This gives us negative 14 meters per second squared as our answer. So those are the instantaneous acceleration of the particle at 1 second and at 2 seconds. So lastly, how do we solve for the area under the curve of an acceleration time graph? So this is an acceleration time graph. Why? Because this is a velocity time graph. This is a velocity time graph. Because obviously we have here the velocity with respect to time function. Right? So this is a velocity with respect to time function. So the graph that we have in here is a velocity time graph. So if we're trying to get the area under the curve of a velocity time graph, we will obtain a physical quantity of position x. So that is equal to the integral of v of t, right, dt, with limits from t sub 1 to t sub 2. Alright, so now how do we solve for the area under the curve of a velocity time graph? So just the first step that we need to do is to copy the velocity time function inside our equation. So this will now then give us the value of integral of negative 4, so negative 4 t squared plus 2t dt with limits from t sub 1 to t sub 2. Alright, now how do we solve for the integral of negative 4t squared plus 2t dt? So the first thing that we need to do after substituting the function into the formula is to integrate using the rules of integral. So what is the basic rule of integral? That's integral of x raised to n dx is equal to x raised to n plus 1 over n plus 1 plus c. Okay, this is the rule, right? So that's what we'll be doing in this one. So now our answer will be Okay, so we will use bracket notation to enclose our whole function. So this will be negative 4, okay, negative 4, so n plus 1, right? So we will be adding 1 into the exponent, so this will become negative 4t cubed all over 3 plus, okay, as for this one, 2t, so add 1 to the exponent, so 2t squared, and then copy the exponent to the denominator, and then close bracket. Now, at the portion of the bracket on the right side, you put there the upper limit. So the upper limit is the t2, right? T sub 2. So that's 2 seconds. And the lower limit is 1 second. So these are the limits of your integral. So after integrating using the rule, you need to simplify if there are things that can be simplified. So if you can see here, we have your 2t squared over 2, so you can cancel this one out. So we're now left with negative 4. So negative 4 t cubed all over 3 plus t squared with limits from 2 seconds and 1 second. Alright, so after simplifying, you can now evaluate the whole function, and we will now integrate the limits into the equation. So the rule here now becomes upper limit first. Okay, so we'll substitute the upper limit first into the bracket minus the lower limit. Alright, so substitute. So this is equal to negative 4 times 2 cubed all over 3 plus 2 squared, alright, minus lower limit. So lower limit, substitute negative 4 times 1 cubed all over 3 plus 3 squared. Okay, so now that we're done with that, okay, we can now simplify this one. So our answer will be negative 20 over 3 minus negative 1/3. Alright, so since this is negative 1/3 and it's preceded by a minus sign, so this will be positive and this will be plus. So let's rewrite it in this side. So negative 20 over 3 plus 1/3. So now, after doing that, after simplifying it, we can now obtain the final answer. So the final answer is that x is equal to, so x is equal to negative 19 over 3 meters, or this is approximately equal to negative 6.33 meters. So this is now our final answer. Alright, so I hope that you learned something out of this video. So see you on the next one.